So as we discussed already, the curl and the Stokes theorem, we now understand what's meant by rotational vector or irrotational vector. An irrotational vector has another name. We call it a conservative vector. And here I thought of showing you some classification of these vectors. So here we have a vector which is pretty uniform everywhere. It does not seem to be diverging from any point. So there is no source for these field lines. So as a result, its divergence of zero is zero. And of course, if we try to build a contour as we explained earlier around any point, you see that the answer will be zero because of the uniformity of the field. So we can simply see here that this field has a zero divergence. We call a vector with a zero divergence a solenoidal vector. So this is called a solenoidal vector. And it's also a conservative field or irrotational field. Both are the same. It does not have a circulation at any point. And you can see it curl is zero vector. This vector here, if you take a look at it, these vector lines, you can see they are all diverging from this point. So the divergence here must be positive. There must be a positive charge, as we'll see later. If these are electric field lines, this means there is a positive charge there. And if you try to calculate its curl, the curl will give you zero because of the symmetry of the field lines. So if you try to build an element around here, you'll see that the integral of this function .dl will cancel out. Some edges will give you a positive answer, the other edges will give you a negative answer with the opposite sign, and they end up with a zero. So a vector like this one has a non-zero divergence, but it's still a conservative field, and it's irrotational field, so its curl is zero. A vector like this one, as you can see, it is circulating. It has circulation form. This is pretty much like the one we get from electric wires. The magnetic field around them looks something like this, pretty much. And do not seem to be diverging from anywhere. And as you will know later, the magnetic field has zero divergence. So a vector like this has zero divergence, so it's solenoidal, but it is a rotational field. Its curl is not zero. The last vector we would like to talk about, just to mention, when both of them are not zeros, and you can see here, this one here, the vector seems to be causing a rotation. It's rotating, it causes circulation, but again, it seems to be diverging from one point. This one here, so the divergence here is positive, and the curl is not zero. So you can get all type of combination of these vectors depending on the source of the vector, and so on. One other important thing that we'll need in this course is a concept of the Laplacian. And the Laplacian of a scalar is a scalar. Laplacian of a scalar is a scalar, and is defined as the divergence of the gradient of that scalar. So if we have V, this is the gradient of V. It's a vector. It has three components: x, ax, ay, and az. The first one is partial v, partial x, partial v, partial y, partial v, partial z. If we take dot product between the divergence, the del operator, dot this one, then you differentiate the x component one more time relative to x, differentiate the y component one more time relative to y, differentiate the z component one more time relative to z, and you end up with this Laplace squared operator. This is what we call the Laplacian operator. And during this course will be one of the most important equations we'll get to see. It's called the Laplace equation. It is equal to Laplace squared v is equal to 0. And this is the equation we use to solve for the potential in a domain where there is some voltage applied and so on. We'll be talking more about this, and you'll see how it relates to electric circuits and so on. And by the way, divergence or the Laplacian have more complicated expressions in cylindrical and spherical coordinates. You obtain them through transformation of variables, and you can look them up in the book. I'm not going to be mentioning them here, and you should include it in your cheat in the for the midterm and the final exams. A number of vector identities you should remember. The curl of the sum of two vectors is the sum of the curls. So if you have curl of a plus b is equal to curl a plus curl b. The same applies to some other differential operators as well. This is very important. The divergence of the curl of any vector is equal to 0. Remember, divergence it gives you a scalar. So if you take any vector, calculate its curl, this will give you a vector. If you get the divergence of that, you get a scalar. this will always be 0. And I'm not most likely, if I give you a question like this, I will give you a vector and then I ask you to verify this identity for it. So you have to obtain the curl, and then you show me that when you get the divergence of the curl, whether it's cylindrical, spherical, or Cartesian coordinates, you'll get 0. Now, this is very important as well because you'll see it later in this course. When you say that the divergence of B is 0, where B here represents the magnetic field, we say, okay, this means that B can be written as a curl of another vector. And this is what we call the magnetic vector potential vector. So this magnetic vector potential is very important in antenna theory, and its origin comes from this identity. That if you have any vector whose divergence is 0, then it can be written as the curl of another vector, because the divergence of the curl of any vector is equal to 0. Another very important identity is this one here, which is saying that if you take a scalar function, calculate its gradient, this gives you a vector. If you get the curl of that vector, you must get a 0 vector. And this one here is very important in electrostatics, because as you will see later, the curl of the electrostatic field is always equal to 0. And this is why we're able to say that the electric field is equal to minus the gradient of V. The minus sign really does not make any difference, because you can multiply both sides here by a negative sign. So this will show up very soon in electrostatics. So these two identities, the divergence of the curl of any vector is 0, and the curl of the gradient of any scalar function of 0, are one of the most versatile and widely used identities in electromagnetics. Now, one other definition I would like you to remember, that the nabla squared can be applied to a vector, and in Cartesian coordinates, this equal to nabla squared applied to the first component in the x direction, nabla squared applied to the second component in the y direction, nabla squared applied to z component in z direction. In spherical coordinates, more complicated, but in general, this is the way we define the nabla squared. Nabla squared of any vector is the gradient of the divergence of that vector minus the curl of that vector. And this one here, this identity here, those of you who will study 3FK4 will remember it later, because this was the one we used to define the wave equation, to derive the equations for waves and when they travel in different types of media. So this is something you have to remember here. This identity, nabla squared E of any vector E, is the gradient of the divergence of that vector minus the curl of that vector. You some application of these identities and so on. I decided to maybe explore a little bit their application here. So the first one is to show that the potential function, we have here a potential function V. It's a function of x and y. It's not a function of z. Sine hyperbolic by y over 2 multiplied by sine by x over 2. Well, I'd like to show that you show me that this one satisfies Laplace equation. And as I mentioned, Laplace equation is a very important equation. It appears in electromagnetics very often, and is equal to nabla squared V is equal to 0. And for two-dimensional problem like this one, this means that the second derivative of V relative to x squared plus the second derivative of V relative to y squared will give you 0. This is what this means. This is what's meant by Laplace equation into the two-dimensional case. So in vector identities, most of the time I will ask you to verify the identity. So here I want to show that nabla squared V for this one is equal to 0. So what you have to do, you have to differentiate it 2 times relative to x plus its derivative 2 times relative to y, and then you show that these two cancel out. This is pretty straightforward. If you first differentiate the sign, will give you cosine multiplied by pi over 2. If you differentiate the cosine one more time, gives you minus sine multiplied by another pi over 2. So this is saying that the second derivative of V relative to x squared is equal to minus pi squared over 4 multiplied by V. The second one is the derivative relative to y. Remember, this is a hyperbolic function. So the derivative of sine hyperbolic by y over 2 is pi over 2 cosine hyperbolic by y over 2. And if you differentiate one more time, the derivative of cosine hyperbolic by y over 2 is equal to sine by hyperbolic by y over 2 multiplied by pi over 2. So you get another pi squared over 4 here. And obviously this term here, by partial squared V, partial y squared, is equal, has a negative sign to partial squared d partial x squared, and both of them are equal to a scalar multiplying the original function, so they cancel each other out. Together you can see the negative term will cancel with the positive term and end up with 0. Laplace squared is used very often, and later in this course you will see when we say these are 4 metal plates. This one is connected to a battery, it keeps it at the voltage of V2. This one, a battery, keeps the voltage V1. This one is a voltage V3, the voltage V4. And I would like you to obtain the voltage at any point inside this domain. And how we obtain it? We obtain it by solving Laplace equation, as I will prove to you later during this course. So Laplace equation is very important to remember. It's very related to electrostatics and the solution of the electrostatic potential. One other example I want to discuss with you is the proof of vector identities, and this is probably something you're going to see in midterms and finals. So I gave you here a scalar function v in cylindrical coordinates is 5e to the minus rho cosine phi, and I want you to show me that indeed for any scalar function, not for this one only, that the curl of the gradient of a scalar function is always 0 vector. The curl of the gradient of any scalar function, and I just picked this one for you. So what you have to do is very simple. First, to obtain its gradient, and once you obtain its gradient cylindrical coordinates, you apply the curl operator to it, and you show me that indeed it does cancel out. Remember, this one here is a function of rho and phi, is not a function of z. So the first step here is to write the expression for the gradient, and this is a gradient, as you could see in spherical coordinates, has 3 derivatives. Derivative relative to rho, derivative relative to phi, and derivative relative to z of the scalar function. The scalar function is not a function of z, it's only a function of rho and phi. So when you differentiate relative to rho, you get minus 5 e to the minus rho cosine phi a rho. If you differentiate the cosine relative to phi, you get minus sine phi. So this will give you this term here, and then you divide by rho, which is coming from the gradient expression. Now, the second step is to get the curl. The curl of any vector b, and here I call b is equal to gradient of v. But just to avoid making things complicated, just call the curl of b. This is the expression of curl of b in cylindrical coordinates. Many things will simplify immediately. Here, this b does not have a z component. Then partial bz partial phi is 0, and partial bz partial rho is 0. You will notice as well that a rho is not a function of z. Then partial b rho partial z is equal to 0. You will notice that b phi is not a function of z. Then partial b phi partial is equal to 0. So this curl will not have a rho component. This is all zeros. It will not have a phi component. It will have only a z component as shown here. So we differentiate b phi, first multiplied by rho, and then differentiate relative to phi. So remember, rho will cancel out with rho here, and the derivative relative to rho will give you e to the minus rho, will cancel with this negative sign. Now you differentiate b rho relative to phi. So if you differentiate b rho relative to phi as shown here, the cosine phi will give you minus sine phi, will cancel out with this one. So if you put these two derivatives together, which are only coming from the z component, this is what you will get eventually. This term here is coming from the first derivative, this term is coming from the second derivative. You see that these two are identical, they cancel each other out and they give you 0. So indeed, the curl of the gradient of that vector is equal to 0, and it does not really depend on position. It is valid everywhere in the space. For any rho, for any phi, for any z, this must be satisfied for any scalar and differentiable function. So I like this type of questions. I may give you some of this in the midterm. I give you a vector identity. I ask you to verify it, and I'm just testing how we are applying the different operators and how we can get different components of the derivative.